Yes. So, in any case, next class will be only online because I would not be in Rio de Janeiro. So that's, the next class on Tuesday will be online. So there is this information on website. I will post it into the group. Yes, but just next time only online. So today I'm going to speak about algorithm which is called QRAM. And the idea of this algorithm is how to upload numbers from classical computer to quantum. So first of all, just a second. Let me recall what we will use from the previous lectures. Yes. So once again, we will use rotations. Oh, I'm sorry. And today for us, the most important rotation will be rotation Y. Yes, so this type of matrix. So we will rotate on the plane, a classical rotation on the plane of two real numbers. Today we will mostly work with real numbers. Yes, and I also will use multiple control rotation implementation. And let me recall, and this is important for the things which are happening, that if we have one ancilla qubit, it's possible to do it proportional to number control bits. So to implement it is a number of operators which proportional to number of control bits. So what does it mean to upload upload numbers to the quantum computer? So assume that we have list of numbers x1, x1, x and minus 1, so capital N numbers, and they are real. Yes, so what to do with complex numbers, I will discuss in the end of the lecture. And such that the sum of their squares is equal to 1. Yes. Then our goal is to create in quantum computer the state sum of xkk. Yes, so we create a vector with those coordinates. This is our goal. Yes. And we will see that this is not so easy operation and that it takes actually more than capital N time, but not much more. Yes. For simplicity, I will assume that those numbers are positive. It's not really necessary. I will tell also together with complex numbers how to upload negative numbers as well, bigger or equal than 0. Yes. So what is the idea? Oops. The idea is to do this step by step. Yes, and here it comes the following situation. So we will first construct a tree and just with those numbers. So on the bottom, like we consider binary tree, yes, so on top we have one element which is divided by two elements, which is further divided by two elements up to the end. Yes, and we will construct it from bottom to top. Yes, so let us consider the lower leaves, the lowest leaves, and let us write the numbers which are squares of the values which we want to upload. So x0 squared, x1 squared, x2 squared, x3 squared, and so on. Yes, and under them we can write the binary representation of the index. So zeros, 0, 0, 1, 0, 0, 1, 0, and so on. Yes, so we have a numbers, and those numbers correspond, like assume that we already implemented, yes, that we uploaded those numbers, then that we uploaded the desired vector. those numbers are probabilities to get this sequence of bits after the measurement. Yes, and let us look onto two sequence of digits which are different only in the last number. So if they are different only in the last number, so we connect them to a node on top of them on the next level. So this was nth level. So we go to n-1 level. Yes, and there we will write sum of the nodes, sum of numbers which are on the nodes below it. Yes, so here x0 squared plus x1 squared, here x2 squared plus x3 squared. And we can associate to this node a sequence of n-1, 0 and 1s. So to this one it would be 3 zeros, to this one it would be 0, 0, 1, and so on. And this would correspond what is the probability to get 3 zeros if we measure only 3 bits. Yes, and so on. Yes, and we go one level up and so on. Unless, until we reach the top, and the top would be sum of all squares of all values, which would be equal to 1. Yes, so then we have this tree. So we construct it. Yes, and this tree would be important in the scheme to construct, to upload the numbers, to construct the state. So let's go. Yes, so let's construct such a tree. Yes, so assume that we have this list of numbers which we would like to upload. Yes. Then on the bottom we will write 3 over 8, 1 over 8, 3 over 8 because this is square of this number, 1 over 8 because this is square of this number, 1 over 4, 1 over 4. And because there are 4 numbers, we have 4 leaves. And then we start to construct a tree on a level higher. Yes, then the sum of those two numbers is 3 over 8 plus 1 over 8. It's 1/2, and 1/4 plus 1/4 is 1/2. And we test ourselves that the sum of all of them is 1. Yes, so this is an example of the tree. So in the end, I also will show the scheme which uploads those numbers there. Yes. Oops. But we will construct the state. We will look on the tree, but we will go not from bottom to top, how we construct it, but to construct the state, we will go from top to bottom. Yes, and let us see what does it mean. Yes, so we have a root of a tree, and there is a value 1 which is written there. And there are 2 branches going from it, one to the left, and this corresponds to value 0, value of the first group is 0, and one goes to the, and another is goes to the right, and it corresponds to the value 1. So assume that the numbers here UL and UR. And by the way how we constructed it, yes, it's the story is that we should UL was the probability to get 0 if we measure the first qubit. And UR was the probability to get 1 if we measure the first qubit. And let us try to make this with the first qubit, and we will make this operation, and later we will never change the first qubit. Yes? And the idea that we are in the initial moment in a state 0, and so we want to have an operation which will move 0 to square root of UL 0 plus square root of UR 0. Yes, just I mean, to get those probabilities, yes, it's not necessary that we have exactly those values, but it would be more convenient to have exactly that. Yes, and okay, we can choose our favorite operation, which do like this. And there is a universal way to do for any values you this is to make a rotation y. Yes, and we can calculate the angle. Yes, and I did the homework. This is 2 r cosine of UL divided by U. Up to now, this is a useless idea to write U because it's equal to 1. Yes, but later we will repeat the similar procedure with other nodes, and there U would be not necessarily equal to 1. Yes, so we start our scheme with the first, with rotation y, with the parameter theta calculated by those values, by these terms. Yes, and then, so we did only one operation with the first qubit, and now we have the situation. So if we measure the first qubit, then the probability to get 0 is UL, and the probability to get 1 is UR. Yes. So next step. Yes, we have a tree. Yes, so up to now, yes, it's we have a. Let us look on 2 qubits. Yes, up to now, the state of the system is that we have here U0 and U1. Yes, and the state is like this, and the second qubit is not entangled, so it's a direct product 0. Yes. And now I want to do the following. So I look onto the value U0. It is decomposed. Yes, so there are 2 leaves under it, UL0 and UR0. And UL corresponds to 1 or 0, and R corresponds to 1. And I want to make the situation so that if I get the probability that I get 2 zeros would be UL0, UL0, and the probability that I will get 0, 1 would be U0R. Yes? And in that case, I would like to do the following operation. So if the first qubit is 0, then I would like to transform the second qubit by this in this form. Yes, and so here kind of I put this U0 square root of U0 in front because if I open brackets, it would be there. Yes, and there is a way to do this, and there's a similar idea. So I looked on a similar. I apply RY gate with a similar calculated angle. So I consider UL0 divided by the 0, consider square root of it, take R cosinus, multiply by 2, and apply Ry with it. So the same as on the first element. But now I will do not just it, but controlled by 0. So if the first qubit is 0, then I apply it. And so this would be controlled Ry, and those 2 not operations make that it is controlled by 0. Yes. What's the next step? I already, like for the 2 qubits, I already made those probabilities correct. Yes. But now I want to make those probabilities. So I consider to the right branch of my tree and would like to make those 2 probabilities correct. So I repeat the same idea, but for this rectangle. Yes, and in that case, I would like, if the first qubit is 1, to make such transformation. And once again, I can, here should be plus. I can calculate the angle, I can make rotation, and apply controlled rotation here. Yes. So now, yes, with such type of scheme, I constructed the correct probabilities for the second, for the first two qubits. Yes, and after this, I go to the third level. Yes, and for each block on the second level, I can see its leaves, which goes below. Yes, and by the similar formula, I calculate, here should be plus, I calculate the rotation angle. Yes, and with this rotation angle, I should execute now multiple controls, yes, which corresponds to the directions of this branch, yes, such that so one in the first qubit, second zero on the second qubit, yes, and I execute rotation. Yes, so this is this block here. And I do this with every node which were involved. So questions?
Sergey, the
Yes.
first one on the top of the tree is the sum of the square is 1, right?
Yes,
It's
the
not?
sum of the square is 1.
Okay.
Yes, so this I have this first one because the sum of squares is equal to 1. Yes, and this is a necessary condition. Yes, because if we don't have the sum of the square is equal to 1, it's not a legitimate quantum state. So we cannot create it. Yes, so this is the situation. Okay, so assume that now I was not lazy and implemented all what I told. Yes. Then let us look how the scheme looks like. I apply RY gate on a first qubit. After this, I applied two control R gates for the second qubit. One was controlled by 0 and one was controlled by 1. If I go to the third qubit, there will be 4 operations corresponding to control by 0, 0, 0, 1, 1, 0, 1, 1, and so on. Yes. So in the end, so on the last element, I would have 2 to the power n minus 1 different operations of controlled by n minus 1 qubits, certain rotation. Yeah, so this is how the scheme will look like. What is good? That the scheme is actually quite straightforward. Yeah, so that's you construct it step by step. There is no some not explicable elements here. Yeah, so it's clear what operation means what. But let us now see how long would be this scheme. Yes, because so if we consider multiple control Ry, that we will need capital O of k, and I write capital O of k plus 1 just for the case to consider k equal to 0 also correctly, because even if there is 0 control, we cannot implement it with 0 gates. Yes. And in that case, so here we have one R1 gate, here we have two controlled RY gate, two square control RY gate. So total number of gates would be of this order. So we have this number of elements, this number of control R operation, and each control R operation takes this time. Yes. So and if you summate this, then in fact it would be capital O of n times 2 to the power n. So this is such formula. And if we think that the capital N is the number of real numbers which we would like to upload, yes, then the number of operations would be proportional to capital N times log n. So it would be asymptotically larger than n. So if we want to upload capital N numbers, we will need to spend time more than capital N. Yes, this is like if we speak about Fourier transform. Yes, so we will. So if we have capital N numbers, yes, then if we want to apply to them quantum Fourier transform, we will have step one upload, and it will take n log n. And after this, the step two, apply quantum Fourier transform, yes, which would be log n squared. So the total number of operations would be n log n plus log n squared, yes, which is just capital O n log n. So this is the thing which I would like to stress attention. In quantum world, sometimes uploading of numbers takes more time than operations which you do with step. And this is a real problem that the interface between quantum world and classical world are not cheap. Yes, so this is computationally expensive. Okay, so the next idea that I will just show how to implement this, show on examples, on concrete examples, how to do this. But before the short comment, how we would upload the complex numbers. Yes, so assume that we would like to upload to create a state psi of this form, where now AK are complex numbers, not necessary positive reals. In that case, we can represent each AK in this form. Yeah, so that's the phase and the absolute value. Yes, and absolute value is at least 0. And as a first step, we just upload such state, which I already explained how to do. Yes, and after this, we just, for every L, we just applies multiple controls, so n-1 control of such a gate, which just changes the face of uh, of 2L index and face of 2L plus 1 index. And of course, this control is somewhere 0, somewhere 1, yes, exactly as the binary representation of L. Yes, somewhere controlled by 0, somewhere controlled by 1. So this is, first we create the whole state, and after this, on every leaf, we change the face. From one point of view, it's quite easy. Yes, this idea is quite easy, but from the second point of view, so if you carefully look onto the lectures which I gave, so I didn't provide for such a gate a algorithm how to make it of capital O of n. So I only provided how to make it capital O of n squared. Yes. So this would mean that it will take a bit more time to upload complex numbers rather than real numbers. Yes, so we will get n log n squared. Yes. So that's basically it. So the rest I would like to consider several concrete examples and to make to show how to create such a state. Let us have 2-3 minutes pause so I can just readjust the computer. But before this, if you have any questions, then you're also highly welcome. Okay, so that's pause for me to rearrange the screen.